Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the next class of CS103 computer programming. In this lecture, I'll be talking about pointers, and this is basically one of the very interesting and important concepts of C++, which you will be using throughout in programming, as you will be using arrays and as well as strings, functions, and other stuff. So, but this is a much more conceptual concept. And in this lecture, I'm supposed to just give a brief or maybe just touch the concept just to a very brief point, and maybe not go in as much detail. Perhaps more detail about the pointers will be given to you in the OOP course, object-oriented programming course, as well as in the data structures course, where you'll be using the concepts and apply them extensively in stacks, linked list, and other structures, as well as in classes. So this is a very important topic for the CS, AI, and CE students to understand. Anyone who wants to do programming probably needs to master the concept of pointers. So without further ado, let's start with the lecture. Um, and yeah, so another important thing is that the slides here are taken from the Detail and Detail book for pointers. I'm not going for chapter 12 in our textbook, because there's not a lot more explanation about pointers in there. Perhaps the author of the book thought that pointers are already clear to the students. But since this is just an introductory class, and this is just the one of the class who's taking their first step towards pointers, so I thought it better to use the same slides from Detail and Detail. So let's begin this lecture. So what are pointers, right? Pointers and strings is basically the topic that is discussed in chapter 5 of the Detail and Detail book, and I'll kind of take that up and discuss the concepts here. This is all about memory. How do you pointers are something that are stored in memory, and we'll be talking a lot about the memory locations and how pointers can access those memory locations, right? So the outline of this particular lecture is going to be introduction, followed by pointer variable declarations and initialization, and then we'll follow up with pointer operators. Also note that in this particular lecture, I will not be giving you separate examples of pointers. The examples of pointers will be pasted within this lecture, and you can basically access them, and you can if you find them appropriate enough, you can just write them out on your own and test them and learn from them. So let's start with the basics of pointers. What is a pointer? How do you access a pointer, and other basic stuff about pointers? Well, pointers is a very powerful but a very difficult concept to master. If you master this concept, you can basically do a lot of uh, very powerful things. But the problem is that you have to master it correctly. You have to understand it perfectly before you can start applying it. Otherwise, this can wreak havoc on your code and on what you intend to do. So pointers typically simulate the call by reference. That is, they usually work in a similar way as a call by reference works in functions. So they access some memory space. They have some memory space to access, and then they access them using the call by reference method. And pointers have a very close relationship with arrays and strings, two things that we studied in the last lecture. So how do you declare pointer variables, and how do you initialize them? Well, pointer variables are certain types of variables that are different from the other variables in the sense that they only contain memory addresses as their values and not actual values. So for example, if you say pointer to an int, so it will not contain the actual value of an int, but it will actually contain the address to a particular int, which will store the actual value. So pointer variables only contain memory addresses, while the normal variables contain a specific value, which is direct reference. So for example, here's an int count, which contains the value 7. On the other hand, if you had a memory address, if you had a pointer variable, it would have contained the memory address to this count. So this is exactly what it is. Pointers contain the address of a variable that has a specific value via indirect reference. So we can actually see that the count pointer has a memory address, and this memory address is pointing to this particular location, which has a certain value. So we can indirectly reference the value 7 using the pointer address that is stored inside the pointer. So what I mean by indirection, you are referencing a pointer value. So this is the indirection stuff. So I can only have the pointer value. The pointer value itself is just a, if you want to reference a pointer value, you use the pointer address, and you can reference this particular value stored inside the variable, right? But you can see the count pointer, which is a pointer variable, it only stores the address here. On the other hand, how you declare pointers? Pointers are basically declared by a thing that we call static. So static indicates variable, that the current variable, whatever it has declared, is nothing but a pointer. It's a specific thing. So you do usually declare it by int static myptr, right? So this line now, if I can write about it, I'll use a laser pointer here. And so yeah, this line, or maybe I'll use some other pointer to make things even better. Let's use a pen, and let's call its color, let's call it red. Yeah, so you see this line over here is going to declare a pointer to an int. So the data type of the data that is stored inside that memory address is an int, and it is a pointer of type int star. So it's a pointer of type int star for referencing that this is a pointer. It is of data type int, and the name is myptr. So you can also declare multiple pointers in the same line, but you need to know that if you declare multiple pointers in the same line, you need to declare them as static myptr1, static myptr2, and so on. So they all should be declared with static. So another thing is we can declare pointers to any data type, be it a simple data type or be it your own user-defined data type, like enums, like any other data type that you can define. You can declare a pointer to that particular data type. How do you initialize pointers? Well, pointers are typically initialized either to 0 or to null or to an particular address, right? So if you initialize a pointer to 0 or null, it will point to nothing. So it's basically saying that this pointer has no address at all. On the other hand, if you initialize it to an address, then there's a specific address that you can access to. So for example, if you want to initialize a pointer to a particular address, you need the address of that particular memory location. And how can you get the address of the memory location? For that, you need to use the address operator. The address operator ampersand actually returns the address of its operand. For example, if int y is equal to 5, right? So y is a variable in which takes up some memory, which takes up the memory of 4 bytes if it's an int. So it takes up 4 bytes and stores the value 5 inside it. So this is what you do when you actually put in y is equal to 5. Then the next line, if you put int static y pointer, right? So it initializes a y pointer, which does not point to anything and at the time of execution of this line. And then you actually give y pointer the address of y. You get the address of y, whatever the address is, you get its address, and then you store that address in y pointer. Notice here that here I'm not using a static operator. Instead, I'm just using yptr. The static was used to declare that this is a pointer of type integer and the name yptr, but the address in it was nothing. So I initialize this address by just simply saying yptr, just like I would access any normal variable y or x or whatever it is, right? So I'll access it in the similar manner, but the value that is going to be stored inside it is going to be an address. Address of what? Address of y. So this now gets address of y inside this. And now wherever I'm going to use yptr, I'll get the address of y as the possible value stored inside it. When you assign it a value, a memory address, it's like it's pointing now towards that memory address. So yptr now points to y. Another example here is, for example, let's say that the value stored in y was 5 and it was stored at a memory address. Let's call it 600,000, right? So for 600,000, the memory address, the address of y is 600,000, and this is the exact value that will be stored in the yptr, which is going to be 600,000. However, note that since you're storing something, the yptr also has a address to itself. So 500,000 is the address of YPTR, but the value stored in YPTR is 600,000, and this 600,000 is something that is the actually the address of Y, which is an int. So YPTR is an int pointer which is pointing to an int Y. Has memory location 600,000. The memory location 600,000 is now stored in YPTR. The value inside Y is 5. So that's the concept here. If you understand this, only then move out. Otherwise, you need to go and recheck and re-verify until you are absolutely clear about how the address is retrieved and how it is stored and what does this particular value mean. What does each of these values mean over here? Okay. So this was how you would reference or you would get an address to a particular integer or variable, right? The opposite of this ampersand is what we call steric sign. Steric is basically the indirection or dereferencing operator. It says that whenever you use steric now, we'll see that it will return the value of what its operand points to. So if it's a pointer pointing to something, a steric is going to retrieve the value from the address stored in the operand. So for example, if you use the steric YPTR, it returns Y in the previous case because YPTR is pointing to Y. So if you are pointing to Y, you're actually going to get the value returned from Y, which is going to be because YPTR has the address 60,000, so 600,000. So it will go to the address 600,000 and retrieve the value. Steric makes sure you go to the address inside it and return the value. If you use just YPTR, it is going to return you 600,000 or the memory location itself. But a steric YPTR is going to fetch the value stored at 600,000. So steric can also be used to assign a value to a location in memory. For example, steric YPTR is equal to 7 is going to change the value in Y to 7 externally. This line precisely is what makes this concept very, very powerful. So with using just pointers, you can actually change the value of any memory address at any place. This is of course a security risk, but this is something that we need to be very, very careful of when working with C++ and pointers in general. So of course, the dereferenced pointer or the operand of steric must be an L value, and it should not be a constant, right? So it must have a certain value and it should not be a constant. So if you, for example, put steric 7, it doesn't work. It has to be basically a variable. You cannot put a direct address over here, for example. Instead, you will have to store the address inside a particular variable, and then the steric operator can work on it. If you put a direct steric 7, it is going to give you an error because it's a constant, and in with steric with dereferenced pointers, you're not allowed to use an L value. So of course, like I said, steric and ampersand are inverses. With steric, you're going to be dereferencing. With ampersand, you're going to be referencing or getting the address of something. So for example, if I've got steric address of my var, how does this operate? Well, it is going to get the address of my var, right? So whatever the address is, it fetches the address. And then from that address, it is going to then apply the dereferencing operator, in which it is going to go to that address and fetch the value again. So you can always do that directly by using my var. Simply, if you write my var, it fetches the value inside my var. The same thing can be done if you use steric ampersand. So this is inverse. It cancels each other because it first fetches the address and then it goes to the same address and gets the value. Similarly, if you reverse it for YPTR, which is a pointer, if you use steric YPTR ampersand, so steric YPTR, basically what it does, it goes to the value, to the possible place and fetches its value, right? And then ampersand is the address of it. So it is equal to using the same as if you just if you just type YPTR. YPTR now also only returns the address that is stored inside the pointer, right? On the other hand, if you want to fetch the value inside the Y pointer, you want to use steric YPTR. But on the other hand, if you want to get the address that to which the Y pointer is pointing to, you can either use YPTR or you can use ampersand steric YPTR to fetch its address. So in other words, these are both the same things. So here's an example. Let's see the code here. So you start with the typical headers, IOStream, using std cout, using std endl, and then you have got the main function running. In here, you declare int a as an integer, int steric aptr as a pointer. A has a value 7. Aptr is now set to point to A. So now you can store the address of A inside the aptr. And then you can simply see out the address of A is so and so, that value of A pointer is this, right? So if you output these two lines, the address of A is m% of A. See that we used m% A. Then the value of APTR is simply the value that is APTR, right? So that we noticed that both the values will be exactly same, because the value that is stored in APTR, which is a pointer as we declared here, hash static APTR, right? So the value stored in it is the address of A. So these two values should be the same. The address of A and the value stored in APTR should be the same. The value of A is A, right? So the value that is stored in A is 7. So we will be getting an output of 7 over here. Then the value of static APTR is static APTR, right? So we'll try to get this is the dereferencing operator. So now we want to go into the address stored inside APTR and get its value. That address is the same as that of A, right? So it will go to the variable A, the address of variable A, memory location of A, and fetch it the value stored there, which will be the same as fetching from A directly. So we'll notice that both answers will be the same. Again, showing that static and m% are inverses of each other. Static, so if we have m% static APTR, the value is like this. And if you try it with static m% APTR, the value is this. And we'll notice that in both cases, so in this case, we actually fetch the address, fetch the value stored in APTR. Whatever is the value fetched there, the value, and then we take the m% of it, and the address of that particular value. So that will be the address of A again. Similarly, if you try it like static address of APTR, we'll notice that this will now go to the address. So this will give us the address of APTR, and then after getting the address of APTR, we then try to dereference it. So whatever is stored in that address, we try to get that, which is another memory location, the memory location of A. So in this case, again, the result would be the memory location of A. And if you run it, so this is just a sample run, the address of A is 006AFDF4, right? So this is the memory address of A. The value of APTR, as we said here, would be the same. We notice that it is the same. Similarly, the value of A and static APTR is same. Then we want to show that static and hash are inverses of each other. We can use m% static APTR. The value is the same as the address of A. Similarly, static m% APTR would also return the same value. And this is what we want to prove. So have a look at this example while I take a minute. Keep looking at it. You must understand the concept of how did I access the memory, how did I access the pointer value, how did I reference it, and how did I dereference it, and why are static and m% inverses of each other. Okay, so I hope you're able to understand this example pretty well. Let's move on to the next example and see how things work. So yeah, so this is again explaining the thing. So this is the address of A. This is the value of A pointer that is going to be stored there. Then if you go further, the static operator returns an alias to what its operand points to. So static is the dereferencing operator. It goes and fetches the value that is stored inside the memory address. APTR points to A. So static APTR returns A itself, right? And A is the value. And notice how static and m% are inverses of each other. So this is also shown here. And then if I run it on my own PC, for example, right? So this is the thing that I'm getting. Int main, int A, APTR, you can notice that it's the same code that is written out. And if I run it once, my address of A is 0x7FF EEE30C7D8. This is so the hexadecimal representation of the memory address. And you can notice that this is what it is, right? So similarly, I've got the APTR as this one, and both are same. You can notice that. Similarly, 7 and 7. And then this is the same address as that of A. So if I run it a second time, This time, you can notice that my memory address is slightly different. It's basically 0x7FFEEB. It was 0x7FF30. On the other hand, this is not triple EB28, so this is a different memory address. Of course, wherever the memory, each time the program is run, it might get a different memory, and that's why you can see that we have different memory addresses. It's not necessary that every person gets the same memory address, and this is something that I will or I can actually ask you in exams. How come that, that for two different runs with the same memory, two different people get the same memory address as their result? That will be one problem I might ask you to catch if you are, asking each other out. So what are addresses and pointers? Well, the concept is very simple actually. C++ allows us two ways of accessing variables. One is, of course, by using the name. So, for example, you can use the name of variable A. The variable A has the name A, right? And what C++ does automatically is that behind the scenes or behind the stage, it is actually mapping each name. So it's keeping a track of the name along with the address of the first location allocated to the variable, as well as the data type of the variable. So for example, if it's an int, let's say int a is the name of the integer. It's a data type integer, so it has 4 bytes, and it is going to be taking up something like uh, it's going to be starting from a particular memory location, and then it has to be read. 4 bytes need to be read so that you can get the exact integer. So, and C++ keeps a track of the first address of the first location. So of the first byte, C++ knows where it is, and then it knows, since it's an int, it needs to read 4 bytes, including that first byte. And hence, for the name, it can know the memory location, and it keeps track of the memory location, and hence it can get the value. So wherever you use a name, C++ compiler automatically converts it into the memory location and then accesses it and gets the value, or stores the value, or whatever operation you want to do with that variable. The other way is in C++, that is allowed in C++, but not allowed in many other programming languages due to the security risk with the pointers, is that it can work with the addresses of the variable. And whenever you talk about addresses, addresses can be used directly by using the ampersand sign, and you can get the variable addresses. Or you can use the pointer variables to store those addresses. So pointer variables are really special in the sense that they know the data type, they know the starting position of the data type, and hence, since they know the data type, they know how many how many bytes they need to read to get the corresponding variable. And hence the other way is that by address or by using the pointers. We have already seen that the symbol ampersand gets us the address of the variable that follows it. On the other hand, the addresses or pointers can be displayed by the cout statement directly as well. The addresses are always displayed in hexadecimal, as we have seen in the previous example. So here's another example. So for example, you have hash include iostream.h, you get void main, you have got an int data is equal to 100, you have got a float value is equal to 56.47. So you store the value, you store the data, cout data, address of data, and next line, cout value, address of value, and next line. And suppose that this is how the memory locations of the RAM looks like. So for example, you have got FFF0 that contains the value 56.47 and its name is value. Similarly, you have FFF4, which is basically the data, and it contains the value 100. So now if you want to access data directly, it's going to give you data and value 100. If you use address of data, it's basically going to give you FFF4. So 100 is going to be output here, and FFF4 is going to be output here. In this case, the output is going to be 56.47, and in this case, the output is going to be FFF0, which is the address of value. So this is the address of value, and that is exactly the output that we get as mentioned over here. And this is the code. If you run the code, and these are the actual memory addresses, you notice that we get the actual memory addresses. These memory addresses are again slightly different, differing at basically the last location. So for example, here it says it runs on till basically 37D, and then this is 8 for the int, and it is 37D4 for the double or float value, right? If you run it a second time, the value is again very different from the original runs. And this is something that you need to know, that every time the program is run, it might be allocated a different memory location. However, we can know the memory location, we can access it, we can use it for our purposes by using the ampersand sign as shown in this example. So the pointer variable is basically a certain data type. The data type contains the address rather than a data value itself. So there's no value inside, if you want to call it. It just contains the address and takes 1 byte of memory. And it is integral. It is very much similar to int, except that the value that is stored inside it is hexadecimal. So it shows it out as hexadecimal. The size of a particular pointer is the number of bytes in which the target computer stores a memory address, right? So for example, if the target computer stores memory address in 1 byte, the size of a pointer data type, whether it is a character pointer or it's an integer pointer or it's a string pointer, it will always be exactly 1 byte, because that is the size it is required to store memory. However, what it knows is that since it's a character pointer or it's an integer pointer, hence the number of bytes that it needs to read from that memory location, that will be dictated by the type of the pointer, right? So pointers provide us the indirect access to values, as we have seen in different examples. How do you declare them? A pointer is declared by data type static pointer var name, right? So you just declare it like that. Whatever the pointer variable name you want to give, you can give it using the pointer var name, and then there's a data type there, right? So yeah, so maybe I just need to change one thing probably. I don't need to use this. I need to have the exact things. Okay, so yeah, um, a pointer variable is declared by this. A pointer variable pointer var name is used to point to a value of type data type. So whatever data type you have, the same type of variable you need to point to. You cannot declare a character pointer and point it to an integer, right? So you need to have a character pointer and point it to a character, a integer pointer point to an integer, a double pointer point to a double, and so on. So the static before the pointer var name indicates that this is a pointer variable and not a regular variable. This is something that I've told you earlier. The static is not a part of the pointer variable name. You need to remember it. This is not part of the pointer variable name. The pointer variable name starts from this point, which stores the memory. Static just shows that this is a data type of, this is a pointer variable and not a typical normal regular variable. So for example, static ptr1 int is a pointer that will point to an integer. Static ptr2 means that ptr2 is a pointer that is of data type float and points to a type float, right? So it's a pointer. ptr2 is a pointer which is pointing to a float variable. ptr1 is a pointer to an int value, that is, it can have the address of the memory location or the first of more than one memory locations allocated to an int value. So if an integer takes 4 bytes, it will just contain the address of the first byte. ptr2 is a float pointer to a float value, that is, it can have the address of the memory location or the first of more than one memory locations allocated to a float value. Again, the same thing, but of data type float. And you need to know that, of course, white spaces don't really matter, and each of the following will declare ptr as a pointer to a float variable and data as a float variable directly. So for example, static ptr comma data, this each of these ones is going to declare ptr as a float, right? So you can see that even if you do it like this, this is a float. You do it like this is a float. You do it in the reverse fashion, this is a float pointer. So these are all float pointers, right? At the same time, data is always declared as a simple float variable. So how do you assign pointer variables? A pointer variable has to be assigned a valid memory address before it can be used in the program. Of course, you need to assign it a proper memory address before you can start accessing the program. For example, float data is equal to 50.8 float static PTR, right? So you declare a float pointer here called PTR, and then you can say pointer is equal to address of data. Store the data, address of data inside the PTR. This will assign the address of the memory location allocated for the floating point variable data to the pointer variable PTR. This is okay since the variable data has already been allocated some memory space having a valid address. Hence, since data has a valid address, you can always get address of data and put it there. So if you run it, and this is how you're going to run it, initially The first line is float data is equal to 50.8. Once you execute it, you have got triple F4 allocated the value 50.8 for data. Then you put declare a float hash pointer. Pointer is assigned a memory address somewhere, so it is triple F0. And then pointer is equal to address of data. This one, the address of data is now input into triple F4, which in otherwise means if you try to access it, we'll try to access this memory location now. So we should not try to assign a specific integer value to a pointer variable, since it can be disastrous. So for example, float hash pointer ptr is equal to 120 is not allowed, or it should not never ever be done like that. It can lead to really disastrous values. Instead, always go for coming up with a data type, storing, declaring a pointer, and get the address of that data type to a pointer so that you are accessing the right thing. However, you should know, so this is a float pointer and you're not trying to point it to an int data. This is also not required because this is a float pointer. It cannot point to an int data, and hence this is also incorrect, right? And this is something that should be avoided as well. Here is what we can do. This is the sample code that we saw earlier. Int data is equal to 100, int pointer value is equal to 120. So notice this thing that I'm trying to access direct memory address. And when I try to basically run it, it says I cannot initialize a variable of type int star with an R value of type int. So I cannot assign it an R value of type int. The int static value cannot be like this. Hence, this is an error. So this gives me a compile time error. It does not let me compile even this piece of code if I try to assign it the value 120 or perfect decimal value. So how do you initialize pointers? Well, a pointer can be initialized during declaration by assigning it the address of an existing variable. So for example, you could say float data is equal to 50.8, float static ptr is equal to address of data. And this is a perfectly legal way and a very good way to actually to give values. So this is, we know, is the same data type as that of this pointer. And hence the address of this data type can be stored in the pointer. If a pointer is not initialized during declaration, it is wise to give it a null or zero value. So you can put it as a null here, right? Or a zero value. So this is always wise to use it like that, so that we know that this does not point to a random value, because it depends on the compiler. Then the compiler might assign it a garbage value, or it might find some value there which we are not intending to read. So what is a null pointer? A null pointer is a valid address for any data type. However, null is not a memory address. So there does not exist a memory address called zero. However, if you use a null pointer, it basically says that I am not pointing to anything, right? So this is not a security risk, a security breach. So it is always, if you try to dereference a pointer by using the static operator, which is basically null. If a pointer is null and you try to dereference it, it is going to give an error. And such an error may cause a program to crash or behave erratically. So it is the programmer's job to check for this. If pointer is equal to null, right, then do not access it simply. So what we generally do is we always, before using a pointer, we say if pointer is not equal to null, then access it, use it, blah, blah, blah. Otherwise, say that the pointer was not initialized and move on with the job. So what is dereferencing? Dereferencing is using a pointer variable to access the value stored at the location pointed by the variable. Like I said, it's basically going to the address and fetching the value there. So this is the dereferencing operator. The dereferencing provides us indirect access to values and is also called indirection. It is done by using the dereferencing operator static in front of a pointer variable. The static operator is a unary operator. That is, it just has a write value accompanying it, which it is dereferencing. And the unary operator and the static, as well as it has the highest precedence over all other operators. So for example, you have got float data is equal to 50.8, float static ptr is equal to hash data, address of data, and then you see out static pointer. So in these cases, we are declaring a float value, then you declared a float pointer data type, then you store the address of data inside the pointer variable, and then finally you want to dereference it using the hash static pointer. So this is the first thing, this is the highest priority. You first dereference it, you get the value of data, and then you basically just see out. And once the pointer variable ptr has been declared, like it is done over here, static PTR represents the value pointed to by PTR. So static PTR now, wherever it is going to be used, you can notice these two are different. These two are the same things, but mean two different things altogether. So in this case, when you are declaring it, it's just the name, right? But other than declaration, wherever else I'm going to use static PTR, it is going to mean the dereferencing operator, and should actually be taken up as a float value itself, right? Like any other variable of float type, if I use a static PTR. But in the first line here, where I'm declaring it, a static PTR means something totally different altogether. It is just declaring a pointer of type float and name PTR. Of course, a pointer is nothing, but it only stores the memory addresses. That's all a pointer is. The dereferencing operator can also be used in assignments. So actually, if you want to use static PTR is equal to 200, if you use PTR is equal to 200, that's not allowed. We saw that's an error. However, if you use static PTR, in this case, this is allowed because this is now going to change the value that is inside the address stored at PTR to 200. We should make sure that PTR has been properly initialized. That's one of the major errors that we get. So we should always make sure that the PTR has been properly initialized. So for example, here's an example here where we are outputting different values here. Float data is equal to 50.8, float static PTR is equal to this, and PTR is equal to address of data. This was what we did before, right? So from this line, if you run the next line, see out PTR. So the value of PTR now should be printed out. The static PTR should be printed out, right? PTR, the value of PTR is FFF4, but the value of static PTR is the value stored at FFF4, which is 50.8. So the answer to this is going to be FFF4 followed by 50.8, and then the next line. So next go to the next line. The next line says static PTR is equal to 27.4. So now we have replaced the value which is stored at the address of stored inside PTR. So at address stored is FFF4. At that address, we go FFF4 and change the value to 27.4. So from 50.8, it now becomes 27.4. And now if we see out the static PTR value, the static PTR now is basically 27.4. And if we output the value of data, it is also 27.4. So the change done by the pointer is a real change. So in that sense, it's working in the similar manner to call by reference, that the changes that are done will be done in real value at real time. And that is why the ampersand sign that I showed earlier is also the address type that I told you. So it's this one is very much connected to that particular examples of call by reference. So here's an example here. This is the same code that we run. So if you run it this time, we get these values. And like I said, this is the address. This is 50.8, the value. This is after you have changed it. It now becomes 27.4, even if you access it by using a static pointer or by using data. And if you run it a second time, the address may differ, but the rest of the things are exactly the same. So let's take some more examples here. And in this case, what we observe is basically initializing a pointer variable by null, and then if we try to access it. So for example, initializing a basic int variable and showing its content and address in memory. So int x equal to 5. See out x is the value of x. We get x is 5, right? And then we see out address of x is address of x, which is going to be some address in memory. So we get the address of x is this, right? Then we have another variable called int static alpha. And when you, so this is a pointer of type int, and the name is alpha, and you initialize it by null. So now if we try to access the memory address stored inside alpha at initialization is equal to the memory address that is stored in alpha. So this is null. So we basically get 0x0, right? Then the line below, this one, where we try to access the value stored at alpha. So the value addressed at the memory stored in alpha is basically the value stored at 0x0. And if you try to access it, this one throws a segmentation fault, and this is what we observe in the code as well. So this line is going to throw in a segmentation fault because we have already initialized this with the null value. On the other hand, let's try to initialize a pointer variable, or let's try not to initialize a pointer variable, and then if we try to access it. So in this case, it's the same thing. This one runs fine. And then we try int static alpha now. So we're not we have not initialized this variable at all. We're not trying to access an uninitialized variable. And then the cout that the pointer at initialization is this, right? So this is alpha. So this shows the address that is stored in alpha. So pointer at initialization is, it does throw up an address. However, then if we try to see out the value stored at address in static alpha, so in this case it runs and it is giving us a value 0. So you know that we didn't initialize it at all. This is what is the security breach here. So if unluckily or by some error we actually started to access the address that belongs to the operating system, or a particular or a very critical file in the operating system, it is going to override that. You can override that using static, as we can see. And because that is possible, this is a huge security risk, and this is something that should be avoided at all costs. So you should make sure that you should always initialize a variable properly. Otherwise, you'll get really strange values. In this case, it was 0, which may not have been desired. Or in other cases, it might be something else, which we do not we do not want to face the consequences of that particular case. So let's try properly initializing a pointer variable and then accessing it. This is the same thing, x equal to 5, value of x. This is address of x. Now alpha is equal to address of x. So alpha after storing address of x is alpha. So alpha after storing address of x is this address. You can see the value inside it, right? The address of alpha is something else. So these two are two different addresses. This is the address of the pointer itself. However, if you want to access the value stored at address stored in alpha, then you need to use a static or dereferencing operator. If you use it, you get the same value that is stored in x. And that's the exact case over here. If you run it twice, you get two different memory addresses, but overall, the result is different. Yeah, so then if you go to the next example where we change the value of a variable using and without using pointers. So these are two particular things. You can change the value of a variable using a pointer, and you can also do it without using pointers. In this case, I take the same example, x will do 5, x is this, address of x is this, alpha is a pointer. We take the address of x and store it into the into this pointer. This is something that we saw before. So now you change the value stored in x directly. This is the direct reference. So this is the direct change, x equal to 10. Now we see that x is x, right? X is 10. Address of x is whatever the address of x we got here would be the same. It won't change. However, alpha after storing address of x is alpha. This won't change either. So the alpha value that is stored, the address of x would remain the same. Address of alpha is address of alpha. The address of alpha and address of alpha would remain the same. However, the value stored at address in alpha is now also going to show value 10, unlike the value 5 that was stored earlier. However, you can do the same operation as you did in this line at x equal to 10. You can do the same operation by using static alpha is equal to 15. And in this case, the value now in x is going to be 15. And the value will be permanent. Or the address will not change, the address will not change, the value in alpha will not change, the value in address of alpha will not change, but static alpha will change to 15 now. The value in x will also change to 15 now. And this is the output that you get from this. And I think this is the final example that we're going to discuss for pointers, and this is something very important again. What happens when referencing and dereferencing operators are used together in a pointer? So if you use them together, they would cancel each other, right? So that's the main thing here, or take home message over here. So int x is equal to 5, and we declare a pointer alpha, that's the address of x. Then we see out x is x, and the address of x is address of x. Alpha after storing address of x is alpha, address of alpha is address of alpha, and then finally the value stored at the address stored in alpha is point alpha. So this one will get us the value of x, which is 5. So this is 5. This is the address of the alpha, and this is the value stored in alpha, which is the address of x, which is the address of x. Yeah. So what happens when referencing and dereferencing operators are used together? If you use them together, the alpha after storage address of x is alpha. So the print value address stored in alpha, right? So I can basically see that if I use ampersand static alpha or static ampersand alpha, I basically get the same result as that of alpha. And this is what we see, the value that is stored. Address of value stored at address stored in alpha. So address of value stored at address stored in alpha is this. So I'm always getting the address of basically my alpha pointer. And this is exactly the same. You can see that this is basically the address of alpha after storing address of x is. So the value in alpha is the address of x. I'm getting that. I'm getting address of x here. I'm getting address of x here again. So this is the same as just outputting alpha, alpha, and alpha, since they both cancel each other. So with that, the lecture on pointers on the basic stuff of pointers comes to an end. I took the liberty to actually talk about it before the other topics because this is a very interesting topic and something that is very useful. You have already seen arrays and you're already aware of it. So I'll kind of I've kind of gotten ahead of uploading these lectures, and I'll upload this lecture first. I have uploaded this lecture earlier than the other ones because this one is kind of a really important and a complex topic as well. So you need to understand it better. However, and you'll probably be needing, you might be wanting to use it in your projects. If that's the case, I think this one is really interesting to you. So with that, I'd like to thank you for listening to this lecture, and I hope that you've learned something about pointers in this particular lecture. See you in the next lecture, where we might talk something about the header files and the templates and what those files are and how we can access them. So take care and Allah Hafiz.